In this video, we are going to analyze an atmospheric column workshop. Through this workshop, we are going to construct, run, and analyze an atmospheric distillation or fractionation column in Aspen HYSYS. This one, okay, so this is our distillation column. We find it from here. Go to separator, and it will be the one absorber with a condenser and a reboiler. Through atmospheric distillation, we have one feed stream. It's heated crude oil, and we are going to have different products like light gas and naphtha and kerosene, diesel, atmospheric gas oil, and sometimes you have a residue. Before the atmospheric distillation happen, we have a desalting unit and a heating. Okay, a desalting mainly separate water and some salts, and after that we heat our feed in a furnace. This one, in this case, it's represented as a heater, but you have here a furnace. So if we go to here and write furnace, so you should have a furnace here. Okay, at all you should have a furnace. This one, this is a fired heater or a furnace. Okay, long story short, this part I'll be giving you this case and you are going to download it, and you will have the atmospheric feed. So let's have a look at our atmospheric feed. Its temperature is 390. This temperature is a little bit high, but if it's higher than this, it's recommended to use vacuum distillation. The pressure here is about 47 psi, or this is almost 3 times atmospheric pressure, but we enter the feed with a higher pressure because inside the distillation column you will have a lot of internal and a lot of pressure drop. This is the composition of the feed. You have a different composition, and also you have here a pseudo components. Okay, it's divided by cuts with different true boiling point, but this is not our point now. We need this stream. Okay, so now we are going to add our column template, but before we need to add a material stream. This material stream will define a steam. Through atmospheric distillation, we also enter a feed, not only a crude oil feed, but also we enter a steam. Okay, so we will have this material stream here, and let me zoom in. Okay, we need this two only, so I'll upload this file to start with, and for this material stream we will have it called a bottom steam. This is our steam, so the composition is mainly water, so water will be 1 H2O. Okay, a lot of times I just find it difficult to find the water composition for. Okay, I think, okay, this is water, so I will add 1 here. So this is our composition, and our conditions, we are given the vapor fraction. It's a steam, so all the stream will be vapor, so the vapor fraction will equal to 1, and we have a pressure of 1379. So the pressure we are given is 1379 kilopascal. Okay, now we don't have the flow rate, so we are going to add it. We have a mass flow equal to 3400 kilogram per hour. Now we have a well-defined stream, and now we are going to add our column. But here, at the beginning, we are going to use a refluxed absorber. Okay, and after that we will add another side unit operations. Okay, so go to the separator, and we will start with a refluxed absorber, or absorber with only a condenser at the top. Okay, so we added our absorber and double click, or refluxed absorber, to open this page. This one is opened by double click, and now we have a column name. We are going to call it our atmospheric column. column, and the number of trays here will be 29, and the condenser is calculated as or mentioned as one stage. Okay, so in this case we will have 29 theoretical equilibrium stage. This is the number of it, and we will also have a top stage, which is a condenser. Okay, we will have to enter our bottom stage inlet, which will be our bottom steam, the stream that we have entered. So we feed steam at the bottom. Okay, and our inlet stream, this is our optional inlet stream, will be the atmospheric feed. Okay, it will enter or will fit at 28. Okay, so the second tray from the bottom. So at the bottom we will feed steam, the one above it we will add our atmospheric feed. After that we will have our condenser. It will be a version condenser with the top stream of gas. So most of the gases from C1 to C4 will be withdrawn from this section, and also any traces from nitrogen or H2S. And we have another overhead product will be naphtha. Okay, so from the top we withdraw a stream, and here it lowers the temperature and it enter a drum. From the top of the drum we have a gas, and from the bottom we have a liquid. It will be divided into two parts. One returned to the top of the column as a reflux, and one will be withdrawn as naphtha. In this case, because we enter a bottom steam, we need to have a water draw. Why we do have a water draw? Because we enter a steam here. In this case, or in this type of atmospheric crude column, if steam is fed at the bottom stage, you must allow an output for this excess water, because you will have some excess water inside the column that might affect the material balance around the column. So you will have a water draw here, and we will call it wastewater. Okay, so now we have this one. From the bottom we will have our atmospheric residue. Okay, so now till now we still have this one not active yet, because we haven't entered the energy stream of the condenser, so we'll call it energy duty or energy Q. Okay, or condenser Q. Okay, now it's active, so we can go to the next one, which is pressure profile. As a pressure profile, you will have the condenser pressure given to be 140 kilopascal, and it might happen a pressure drop equal to 60 kilopascal inside the condenser. And at the bottom stage we don't have a reboiler here, so at the bottom stage we are having a pressure of 230 kilopascal. Okay, so the pressure decreases through from the bottom to the top. And before, if we go back here, we have defined pressure for this one and this one too. Okay, so we have an integration of pressure here. So after entering the data of the pressure, we move forward to the optional estimate page. In this case we have some estimated temperatures. So for the optional condenser temperature, we have it to be 40 degrees Celsius. The top temperature is 120. What is the difference? That this temperature is 120. And after going through the condenser and lowering the temperature from the top of the off gases and the naphtha will be 40 degrees Celsius. The bottom temperature, because we don't have a reboiler, we are giving it to be 340 degrees Celsius. So this is our estimates. Moving forward here, you can sometimes you are not given any data here, but in this case we are having a vapor rate of 0 kilogram mole per hour. Okay, so this is our vapor rate, and after entering it we press OK. We will have our column not converged because the degree of freedom, we go through monitor to check our degree of freedom, and in this case it's mentioned to be 0 but it's not run because here you select this 2 as active and you are not given its value. So in this case we will remove active from here and we will activate this one. So the degree of freedom will be 1, which means you need one more information for this column to be fully convergent. After unchecking the reflux ratio and the distillate rate and checking the vapor product rate, we will have a degree of freedom equal to 1. In this case, we need only one information. We are given here that the distillate rate is 150 meter cube per hour. So we have this value, so double click to add it. The distillate rate, which is related to the naphtha. In this case, we don't have it as a molar, we have it as a volume. Okay, standard ideal volume or the volume at a standard condition. In this case, okay, what is the difference here? This is the standard ideal volume, but in this case, you have a volume but at standard conditions. We are not given here a standard conditions, which is atmospheric pressure and 60 degree Fahrenheit. So it will be the standard ideal volume, which is equal to 150 meter cube per hour. Okay, after adding this one and activated it, okay, after adding it, still degree freedom equal 1 because we need to activate this one. So after activating it, it will be automatically converged and doing all the calculation. As we did before, we can check our results from the worksheet or the performance, but before moving forward, I have a question here. So if you are asked about the volumetric flow rate of the naphtha products, for example, how to find this one, we can go to the performance here and you have here the composition. Okay, for the column profile you have also the temperature and the liquid flow rate. But this one is a mole flow rate. Okay, so you can have it for the ideal. Here we are asked about the ideal liquid volume. Okay, so if we press here the ideal liquid volume, and we know that we have a composition. So we have ideal liquid volume and the condenser. We took our naphtha from the condenser, so this is the net draw. So it will be 153.37 meter cube per hour. So if we are asked about the standard ideal volumetric flow rate of the atmospheric residue product, the residue is taken from this tray and we go to the net feed. This is the outlet, which is 3.4. Okay, and from this one, this is the net feed. This is the feed that is entering. This is the one from the crude and this is from the steam. This is the net draw, the one that we are removing from the last tray will be 460.64 meter cube per hour. So it's important to know the unit that we are asked about. So if we are asked about the mass withdraw, this will be the unit in kilogram. And here we don't have any feed except for these two trays. We have also information about the feed and the products here. And you can have any plot that you want. And for the worksheet in this one, you have some information. Like if we look at the naphtha here and the standard ideal flow, this is another method to find the information. So if we are asked about the standard ideal liquid volume flow, you will find it 150 in this one, and the standard ideal volume flow is 460. These are the same, but there is a slight difference here. Okay, 153 from the previous one. Okay, so now we are finished with the atmospheric column data entry.